bus, unquote. And then there's a crossbar between buses that house the cores and the portions of the L2 cache that are distributed throughout the chip. And then also there's a relationship between the portions of the L2 cache and the DRAM controllers. So we found with this this technique, the crossbar interconnect easily scales to 32 cores. And actually, I showed you previously a slide with 48 core devices, and we believe it easily scales to 48 cores as well. It gives a very low latency, very high bandwidth interconnect with deterministic latency. So software doesn't have to worry about where things are located. Everything is the same distance. Every core is the same distance from, largely the same distance from every memory location, which is a simple software model, even though we have a 32 core device. There's actually a picture of the 32 core device, and if you look closely, the picture is very similar to the block diagram I gave you on the previous slide. So here's 8 cores, 8 cores, 8 cores, 8 cores. In between here and here are those things I call buses. And in the middle is the L2 cache, the crossbar, the DRAM controllers in the middle of that design. So that's actually the majority of the chip area. On the left side is what we call the max and coprocessors. So all those green things on the block diagram that I showed are all fit into this area here. We try to build our designs so that most of the area is consumed by compute capability, and I think we succeeded in this case, and not so much consumed on what you might call I/O capabilities. This device has, it's approaching 1 billion transistors, 700 million. Its power is 40 to 65 watts when you're using all 32 cores. Frequency is up to 1.6 gigahertz, and this design was built in a 65 nanometer CMOS technology. So we're about in the middle now, onto power scalability. Power is very important when you have 32 cores. So many processor cores. If your processor cores are very inefficiently using power, the system will suffer. And what this pie chart shows is we have this crazy application we call power loop, and this would be familiar to any processor chip designer. It is a piece of software whose end goal is to maximize the amount of power consumed on the device. It's not necessarily a useful piece of software, other than it illustrates what's the worst possible scenario for our device. And this pie chart shows how the power breaks up into different components of the processor. At 1.6 gigahertz, this core, an individual core, is 1.28 watts, and we don't, even though that's not too bad of a number, we don't like it. We think that's way too much, and we'd like that to be a lot less. And what I'll show you is some tricks that we did in the design to reduce that amount. The trick is what we call our power optimizing technology. We do have per CPU, we estimate the dynamic power, and I'll show you how we do that on the next slide. We compare that estimate to a dynamic threshold, dynamic power estimate to a threshold. We have both a hardware threshold and a software threshold. The software threshold is just in a register, so software can quickly and easily change it if they desire. So the reason the hardware threshold exists is to limit the worst case power, so that 1.28 watts that I told you about that's the trick that we're going to use to limit that. And I'll show you more in the next couple slides. Software, additionally, software can use their threshold to do an open loop reduction of average power, or you can have a closed loop system with say a thermal sensor where you monitor the temperature and make sure that your temperature does not exceed a certain value. So here's how we get our power estimate. So on the left here, you can look at those as pieces of the core, and there's events going from the, I guess, the orange cells to our what's a device that's called the average unit power table in this diagram. So the idea there is an event. It might, for example, be instruction issued. That's an event. Or I did a load. The instruction issued was a load. Or this clock in the multiplier was running. That might be an event. For every event, we have we calculated from simulation and then validated it in real hardware the amount of energy that's consumed for that event, and we put that amount into what's called here the power table. So we take the event, and that each event consumes a certain amount of energy. We accumulate the energy, sum it, and integrate it, and then that gives us an estimate of the energy. We compare that to both the user input and the hardware threshold is not shown in this diagram. When we think the power has exceeded our threshold, then you see the stall signal in the bottom wraps around back in and controls issue, and we slow down issue of the processor to prevent it from consuming more dynamic power. So what is that bias? Well, there's two interesting aspects of that. And one here, the left diagram shows it's important that our estimate correlates to the actual consumed dynamic power, and the left graph shows that yes, indeed, for a variety of applications, there's very good correlation. Another interesting thing you can see from this diagram is that there, for any given application, there are a lot of different power levels from this core. You have what power goes from like 0.1 on this diagram up to 1, and guess what that guy up on the one up in the right corner that's 1 and 1 is? That's our friend, the power. And you'll notice there aren't very many things up in that upper right corner. And that's what the right graph is showing us also. So the right graph, we show the power as a percentage max of our power loop. Power loop is our worst case one. And what you might consider typical applications, like there's a benchmark called core mark, or there's a dry stove benchmark, or insert your favorite benchmark. The idea is that most applications don't come anywhere near consuming that 100% of the power. So what we can do by putting in, say, a hardware limit to 65% or whatever the right number is you like in this diagram, instead of having to build your system, your chip, and everything for a value of 100, you can build your chip and system for a value of 65, and that's a big difference in the amount of power you need to be able to supply on the board and heat you need to be able to remove from the system. Since we have this hard limit on the power, we can have a hard limit on the power consumed by the chip itself. So that's a big benefit for us. We don't want to design our power system for an application like power loop, which isn't really practical. We want to build. We want our users to design their systems for a practical power consumption level. So there are a lot of pluses and minuses, but some nice things about this technique compared to the very common dynamic voltage and frequency scaling out there is with this technique you can have very fine-grained core-by-core power control. You can, a low-power application is not penalized. So, for example, if you reduce power by reducing frequency, that slows down every application, not just those that are consuming a lot of power. And the implication here is that that's important because most applications don't consume a lot of power. This very fine-grained power control, the settings can change instantly by software just writing register, and ultimately leads to a simpler system and chip design than a DVFS solution. So moving on in our agenda, so we have hardware in the 68XX device that does work queuing of work, scheduling of work to the MIPS cores, does synchronization, offloads synchronization from the MIPS cores, and also offloads ordering from the MIPS cores. Oops. Backwards. There we go, that's better. So this picture shows, so we're, Octane is largely targeted at networking, so we think of everything in terms of packets, right? So this shows a diagram of packets over time. So first, a packet from the yellow stream comes in and gets scheduled to core 0, the yellow flow, you could say, or stream, whatever you want to call it. And we have different flows, the gray flow, the red flow, the blue flow, and such, that over time come into the chip. And we want to ultimately get scheduled in the core. The interesting thing in this diagram is it shows two yellows there. So what does the two yellows mean? For example, those two yellows might be from the same flow. And so you might actually have a synchronization problem if those two yellows were scheduled to two different cores at the same time. So you may want to be clever in your design and only schedule things to cores that aren't going to have synchronization problems. So that's one aspect of it. The other aspect is you're just offloading a lot of queuing and quality of service scheduling from the cores. The way that the Octane solution works is you calculate what's called a tag for every packet. So for example, a tag for a TCP packet would be might be a hash value of the standard 5-tuple. You know, 5-tuple is source address, destination address, all those source port, destination port protocol. So you just take all those bits and you hash them together and you come up with a tag value. And the interesting aspect of that is that those two yellow packets in this diagram would have the same tag value. And so the hardware can recognize that, hey, if there are two things that are the same tag value, that may mean that I need to synchronize or order those packets. So that's one aspect. The other aspect is the hardware can do smart load balancing to the different cores. So we have this schedule, synchronize, order piece of hardware that is co-processor, kind of intimately tied in with the MIPS cores. They have work queuing, so work can be created by software. It can be created by hardware. For example, a packet arrival creates work in the Octane design, and this queuing can be of unlimited size. The hardware can enforce ordering constraints. It can enforce automatic synchronization constraints. For example, you can configure the device so that two packets from the same flow never get scheduled to the same core, to two cores at the same time, which will allow you, for example, not only to offload the work queuing and scheduling from the MIPS cores, but you can, if you're configured that way for those flows, you don't even need to do any synchronization at all. You can just go ahead and write straight line code without any synchronization, and therefore your MIPS cores will run faster because the hardware unit is doing the synchronization for you. Dynamic work scheduling is very important. the algorithm that the hardware uses to decide which packets get scheduled to which cores is very complicated and would be very difficult to do in software, but is well suited to hardware. It includes techniques like, for example, different cores can receive different work. Not all cores are considered equal. And the scheduling algorithm is integrated with the ordering and synchronization. So here's an example of what you do not want to do. So in this slide, different things from the same flow are the same color. So in this scenario, it turns out that I have 4 packets, or actually more than 4, packets from the yellow flow. They came in, and let's say I was dumb and just scheduled it to those first n packets to the first n cores. Well, if there's some synchronization requirements between those different cores, that might not work out so well, because in this example, all the cores, one core has the lock, or whatever you want to call it. He has access to the data structure for the flow. But the other cores may be stalled, sitting there waiting for access to that, so your performance would be really bad. So what you really want to do is you want to take the packets from, in that scenario where you do have synchronization constraints between multiple packets from the same flow, you want to essentially create different queues for the different flows. And that's what our schedule sync order hardware does. Is the packets come in, they get ordered based on tag into lists corresponding to the tag, and things can be scheduled from out of order relative to the order that they came into the machine. In this scenario, you probably only really care, you don't care about the order of 2 packets to different flows. What you care about is the order of about the order of packets to a single flow. So if that's what you want, then the schedule sync order is free to schedule those yellow, blue, red, and green internal FIFOs in any order that it sees fit. So this is an example of techniques that we put in the hardware to make sure that our design can scale well for the applications that we are targeting. And by scale here, I mean it's a 32-core device, and you'd like that to act like a 32-core device and not a 14-core device. Oops, go backwards again. So another important aspect of the Opteon design is coprocessors. There are many kinds of coprocessors in the Opteon device, all of which, as it turns out, are well suited for networking application, encryption, decryption, memory allocation, compression, decompression, network search algorithms, regular expression processing. So we think accelerators like this are very important. One reason for that is that we don't want to just throw all of our resources at very complicated cores and making them power efficient. We want to do things, we want to do work on hardware where it's efficient to do that. If the MIPS cores are an efficient way to solve a problem, then we will do the function there. If, for example, you want to do compression and decompression, the MIPS cores are a very inefficient way to do that algorithm, and it makes a ton of sense to have hardware on the chip. It'll be faster and a lot lower power for the application. So there are a lot of different types of accelerators, but I'll zero in this talk on one type in particular. We'll classify it with the general category of deep packet inspection. There are many applications that need deep packet inspection, amongst them including intrusion detection, packet classification, and such. And there are a number of things that you need to do deep packet inspection well. You may need to reconstruct a TCP stream, for example. You may need to do other things that are necessary in order to be a good packet inspection device. Octane has a lot of things to accelerate those other things too, but in this next few slides, I focus strictly on the pattern matching portion of deep packet inspection. The idea of deep packet inspection is you may have certain patterns in the packet that you want to be able to identify quickly, and when those patterns exist, you might change your processing. So for example, in intrusion detection, it's possible it's an indication of an intrusion if a certain pattern is detected in the packet. The percentage of data that needs to be scanned for pattern matching varies a lot for the different applications. For applications like intrusion prevention and antivirus, you have to scan most packet bytes. For others, like where you're just trying to figure out what kind of application it is, you may only need to scan a few percent of the actual packet data. For those devices, for those applications where you need to scan all the packet bytes, it's a very difficult computational problem to be able to keep up with the line rates of the data coming in. So the way it works is the patterns that you're searching for are often regular expressions. They're pre-compiled into state machines, hardware state machines that are written into the various memories in the unit. And the solution includes compression of the graphs and caching to maximize coverage and performance. So the architecture of the design is actually shown here. The unit that does deep packet inspection in 68XX we happen to call HFA, the FA for finite automata. What we have is 3 clusters of 16 engines for pattern matching. So you can look at this as an additional 48 cores on this device that are dedicated for pattern matching. So these cores can be pattern matching, which is what they're good at, while the other cores can be doing the other important stuff that they need to do. Within each cluster of 16 engines, there is a local cache. And then when that cache is exceeded, you have to sometimes get the patterns, the graph, whatever you want to call it, from the DRAM interfaces. So we have on the chip a special HFA DDR3 interconnect to get to memory. So when packet data comes in, it ultimately comes through the top in this diagram. The state machine is walked by accesses to the caches, by accesses to the DRAM, and then the results are sent back to the MIPS cores via the top again. So at the top is the CPUs, the packet data and results, and at the bottom part of this is the state machines, the memory for the state machines. So we're now on to some performance results. So a simple application for Octeon is what we call IPv4 packet forwarding. So you receive an IPv4 packet, you do a lookup to figure out what to do with the packet, and you send it out. And the interesting thing here is the I/O limitations of the device are 40 gigabits, and the internal processing for this type of application is much more than needed. You only need about 4 cores. You're up to 4 MIPS cores, and you're up to a 40 gigabit limit of the I/Os of the chip. And you have 28 cores to do other advanced processing, maybe deep packet inspection, maybe whatever. Another application that's one of the common applications of our Octeon device is a full IPsec application. Some of you may be familiar. IPsec is a way to tunnel IP packets from, for example, this campus here at CMU to another campus at CMU to have a dedicated connection that's that's tunneled and encrypted. So this data shows on the left the bandwidth, which for packet sizes 300 bytes and up. Again, we can satisfy full 40 gigabits bandwidth of part. And on the right, for minimum packets, it shows the scalability of the processor cores, and there is one of the places where you see the advantages of our scheduling techniques. The scalability is almost 32. I think it's like 31.8 speed up by having 32 cores versus 1. So it's very close to linear scalability, which we think is very important for a device that's this capability. You don't want to waste your processing. So this is the conclusion on the main portion of the talk. At Cavium, we have been applying multi-core products to networking server and other markets for a number of years now, successfully. We discussed the Octeon architecture and how it has efficient CPU cores, scalable interconnects, its power capabilities, hardware queuing, scheduling, synchronization and ordering, and co-processors suitable for target markets. So maybe now is a good time to take questions on the first part of the talk. Yes?
Do you have performance results for applications that actually exhibit the ordering and synchronization aspects that you mentioned?
Well, the IPsec application actually is one that exhibits that exactly.
So ordering is an issue there, it's not embarrassing
yes.
in parallel? Okay.
No, it's not. Those were a small tunnel count. So we had a bunch of packets to the same tunnel, so it was a perfect example of that.
Okay.
Yeah.
So I'm curious about this don't write back thing. So are you saying that a core might write some data to the cache and create a dirty cache line?
Yep.
But then somehow you know that you're not going to use that again, so you can sort of say...
Yeah. So for example, that core, when it writes the data to the cache, might be creating packet data. And it may know that, furthermore, so that packet might get sent out of the chip. And it may be that once that packet is sent out of the chip, we know, hey, I'm not going to need that packet data.
So the core is reading it. But
So
it
the core writes it, and then the hardware is what actually sends the packet out. We have memory allocation hardware in the device. So the software would have told the hardware in this case, hey, after you send the packet, you can go ahead and free it. Free this memory buffer. So the hardware knows when a memory buffer is getting freed, that means that, hey, I don't care about any of the data in this buffer. So it can issue these commands we call the don't write back and make sure that we don't frivolously write back data to the DRAM.
So from the cache's point of view, it's like a scratch pad almost. You're saying it doesn't have to be coherent with memory. You can just throw away whatever.
That's right.
Okay.
That's right. That's right.
Do you have to lock it?
So effectively, we make after the don't write back, we make the value of the cache block unpredictable until something writes the cache block again.
Okay.
Any other questions? Yeah.
Are you going to talk more about Project Thunder in your subsequent part? Or?
No, I can't really say much about Project Thunder. It's a fairly new thing for us. We are well engaged in Project Thunder, but I can't. Not much has been announced about it yet, and I can't really discuss that very much. Other than, as I mentioned, it's an important thing to us. We're moving into an adjacent market, the server market, instead of our. In addition, I should say, the server market in addition to our traditional networking market. And number two, it is a movement toward the ARM 64-bit instruction set.
Right. Yeah, there is a blurb actually on the Cavium website about
That's
that.
correct. That's correct.
So I guess I would be curious to find out what sort of applications and workloads you would have that processor target. Is it generic, or do you have something specific in mind?
Well, the device, the original Thunder device that we're targeting is for cloud type applications. So we have been in contact with a number of potential customers, and we are in discussions with them and have a good idea of what the features we are going to support in the device. Actually, we know exactly what it is in the device.
But you cannot say what that is.
But I can't say what that is.
Okay.
Sorry.
Hopefully it's more than just hardware and network virtualization.
That's correct.
Okay. All right, thanks.
Yeah.
Your slide that motivated the hardware-based scheduling
Yeah.
of the streams